AI Financial Portal number 2. We're going to talk about the LLM competitive advantage, how code generation and prompt engineering accelerates software development. Let's take a look over here at our chatbot, and we ask it to give us the Python code that generates a graph of the 5 highest mountains in the world using Matplotlib. Now, as an experienced Python programmer, if my boss came to me with that, I would say it'd take an hour, maybe 2 hours to put that together and make it look nice. In 30 seconds, I can generate code to plot this out with our LLM, and when I basically copy and paste the code over here, it's about 30 lines of code here, and I go and click on run over here, and it puts out this graph here, the 5 highest mountains in the world. And you can see that barely, these are all pretty close together, and the Y scale is not very much to our liking. But boss said he wanted a graph of the 5 highest mountains in the world. There are the names of those mountains, and there's their height. Now, since we know how to code, which is really crucial in this whole code generation and prompt engineering, because the prompt engineering allows us to tell the LLM what kind of code we want it to generate. So this is what it did. And after looking at this for a little bit, I actually came up with something a little bit better. And so when I run my improved code, I get this. I have the mountain range names. I've put the numbers so I can see exactly how high it is. It's in meters. I can switch it to feet if necessary. It has a nice color code, and this is easy on the eyes. So it takes an hour. This would take 20 minutes with the draft code and then tuning it up. So we saved an hour. Now, if we go over here and look at our Black-Scholes code, we have the Black-Scholes call, and what we need to do is to find out what is more efficient for our Black-Scholes calculations. So we're going to compare the processing times for TensorFlow versus SciPy. We'll also be able to calculate the Greeks. We're not doing that right now. We're going to talk more about the Greeks. But what we're trying to do with this little bit of code is to get some benchmarking for TensorFlow versus SciPy Black-Scholes calculations. Because when we're handling large portfolios, speed is going to be important. So here's my code to read some synthetic data I made. And these are the tickers. There's a put in there, the calls and puts, the strike, maturity, volatility. I pulled the options chain, and I stored it in something called options portfolio CSV. This data is synthetic. I'm going to time the Black-Scholes. This is the formula for Black-Scholes using the SciPy. And now I can calculate the prices. We have the risk-free freight here. Here's the SciPy execution time. And then I run the same data set with TensorFlow execution time. And so for 15,000 options, I can calculate the price in 1.4 seconds with SciPy and about 12 seconds with TensorFlow. That is nice performance. Well, what if we have 150,000 options here? I want to calculate the Black-Scholes prices. We'll talk about how these prices are in a closed form calculation, so there is only one answer. So it's a calculation. So if I do 150,000 options, same code, which I've generated with the AI, and I've validated it, I can do 150,000 options in 12 seconds and about 2 minutes for TensorFlow. We want to know how long TensorFlow takes for SciPy, because SciPy is not going to be able to do the binomial pricing model. We'll have to go with TF. So let's look at 500,000 options here, and we run it through, and it takes about 40 seconds for SciPy to calculate this. In TensorFlow, it takes almost 7 minutes. We're going to be able to get the Greeks out of here. We're going to do a lot of things here. But trying to write this code out line by line, this would take weeks. It would take weeks, okay? You got to be drafting this stuff with AI. Thanks for your time. Much more to come.